Hello everyone. Welcome to SHR Trinity. In our previous video, we explored zero-shot prompting. Today, we advance to the next critical technique, chain-of-thought prompting. In this video, we will cover the foundational interview questions on chain-of-thought prompting, explaining how providing just a single example can drastically improve a model's accuracy and format adherence. Let's get started. Before we begin, if you're looking for practical, industry-oriented training in artificial intelligence and generative AI, SHR Trinity offers a comprehensive 30-hour training program. For complete course details, check the description below. Now let's begin today's interview session. We will now begin with the interview questions for chain-of-thought prompting, Part 3, Self-Consistency and Majority Voting. Question 1. What is self-consistency in chain-of-thought prompting and how does it improve reliability?
Self-consistency is an advanced prompting technique introduced by Wang et al. In 2022. It replaces greedy single-path decoding by sampling multiple diverse chain-of-thought reasoning paths and picking the most consistent final answer via majority voting. Complex reasoning problems often have multiple valid ways to reach the correct solution, but greedy decoding can pick a single flawed path. By sampling diverse reasoning paths at temperature zero, correct answers naturally emerge as the statistical majority. For example, sampling 10 distinct CoT reasoning paths for a math puzzle, 7 paths arrive at 42 foot, 2 at 40, 1 at 45. Majority vote selects 42 foot. A common mistake is running self-consistency with temperature set to 0.0, which produces identical deterministic paths and destroys diversity. As an interview tip, explain self-consistency as an ensemble voting technique applied to inference time token generation.
Question 2. How does self-consistency replace greedy decoding with sampled reasoning paths and majority voting?
Greedy decoding selects the single highest probability token at each step, temperature equals 0. Self-consistency uses stochastic sampling, temperature equals 0.5 to 0.7. to generate n independent CoT reasoning paths, aggregating final answers through majority voting. Stochastic sampling allows the model to explore different logical entry points and intermediate solution strategies. Even if individual paths contain minor errors, the consensus across independent paths filters out stochastic noise. For example, Path 1 uses algebraic substitution, Path 2 uses graphic breakdown, Path 3 uses trial deduction. All three converge on the same final numeric answer. A common mistake is assuming self-consistency requires fine-tuning model parameters, when it is strictly an inference time decoding strategy. As an interview tip, highlight the parallel. Self-consistency is to LLM reasoning what random forests are to decision trees.
Question 3. Why does generating multiple reasoning paths resolve stochastic errors in complex math problems?
Welcome back. Today's question touches on a crucial property of language models. Why does generating multiple reasoning paths resolve stochastic generation errors in complex math? You see, autoregressive language generation is inherently probabilistic. When a model generates a 50-token mathematical proof, it evaluates probabilities at every single token step. If there is a 5% chance of making a minor sign slip or arithmetic error on any given token, a long sequence carries a high cumulative probability of failing. Under standard greedy decoding, that single early error permanently derails the rest of the output because future tokens are conditioned on that incorrect step. Self-consistency mitigates this compound risk through path diversification. By sampling multiple independent branches, we statistically guarantee that uncorrupted, error-free paths will exist in our sample space. Because mathematical logic is deterministic, all correct reasoning chains will naturally converge on the identical ground truth value. Conversely, random calculation mistakes drift off in unpredictable directions, resulting in fragmented, low-frequency wrong answers that lose during majority voting. Let's walk step by step through our example to see this in practice. Consider a multi-step probability puzzle. Under single-path greedy decoding, the model makes a sign error on step 2, leading to a completely incorrect output. But when we apply self-consistency and sample 10 independent paths, 8 of those paths avoid that sign mistake, some by organizing the variables differently, others by double-checking intermediate totals. Those 8 paths all output the correct answer, easily outvoting the 2 corrupted runs. This illustrates how multipath sampling isolates and discards isolated generation glitches.
Question 4. What is the optimal temperature setting and sample count, K, for self-consistency decoding?
In empirical research, the optimal temperature for self-consistency sampling is between 0.5 and 0.7, and the sample count, K, is typically between 5 and 10 reasoning paths. Temperature equals 0.5 to 0.7 provides sufficient path diversity without causing the model to generate nonsensical gibberish, which happens at temperature greater than 1.0. A sample count of 5 to 10 captures majority consensus efficiently. For example, setting temperature equals 0.7 and sampling K equals 10 CoT paths yields a 10 to 15% accuracy boost over single-shot greedy CoT on GSM-8K. A common mistake is sampling 100+ paths per request, which leads to massive API cost inflation with diminishing accuracy returns after 10 to 15 samples. As an interview tip, mention that K equals 5 to 10 represents the sweet spot for balancing API cost and accuracy gains.
Question 5. How do you implement majority voting when model outputs are free text explanations rather than numbers?
For free text outputs, majority voting is implemented by clustering semantically equivalent answers using an LLM evaluator, embedding similarity, or extracting a standardized final answer key before counting votes. Unlike simple math where answers are raw numbers like 42 foot, text answers might say the policy is active, policy active, or it is active. Embedding cosine similarity or an LLM-based grouping step aggregates these into a single vote category. For example, using embedding clustering, threshold 0.85, to group free text responses into 2 primary clusters before applying majority count. A common mistake is using exact string matching on free text answers, which causes identical semantic answers to be counted as separate votes due to minor wording differences. As an interview tip, advise extracting a normalized short answer key at the end of each reasoning path to simplify majority counting.
Question 6. How does self-consistency impact total token usage and API cost per request?
Self-consistency increases token usage and API costs linearly by a factor of n, where n is the sample count. Generating 10 sampled reasoning paths increases input and output token expenses by 10x per request. Because each of the n paths is generated independently from the prompt, processing n requests consumes n times the completion tokens. For 10 paths of 300 tokens each, you consume 3,000 output tokens instead of 300. For example, a system processing 1,000 queries daily at 2 cents per call, $20 per day, jumps to $200 per day when using 10 sample self-consistency across all calls. A common mistake is deploying self-consistency on high-volume low-margin production endpoints without analyzing unit economics. As an interview tip, highlight optimization techniques like parallel async API calls or dynamic sample stopping to reduce self-consistency costs.
Question 7. In what mission-critical enterprise applications is self-consistency mandatory?
Self-consistency is mandatory in high-stakes, mission-critical applications such as automated medical diagnosis coding, financial compliance verification, legal risk assessment, and safety-critical engineering calculations. In high-stakes domains, a single hallucination or calculation error can cause severe financial loss, regulatory penalties, or safety hazards. Paying a 10x token premium for 99% plus deterministic accuracy is completely justified by business risk reduction. For example, an automated loan underwriting system evaluating $50 million commercial credit applications, where a single miscalculation causes massive financial exposure. A common mistake is skimping on token costs in safety-critical pipelines where accuracy failures carry huge real-world liabilities. As an interview tip, frame self-consistency as an essential AI risk insurance policy for enterprise applications.
Question 8. What is weighted self-consistency and how do you weight reasoning paths by model confidence?
Weighted self-consistency is an enhancement where instead of giving each sampled path one equal vote, votes are weighted by path confidence scores, log probabilities, or step-by-step reasoning quality metrics. Not all reasoning paths are created equal. A path generated with high cumulative token log probabilities or explicit self-verified confidence, e.g. confidence, 98%, carries more mathematical weight than a low probability path. For example, path 1, weight 0.95, votes A, path 2, weight 0.90, votes A, path 3, weight 0.30, votes B. Total weighted vote heavily favors A. A common mistake is treating low-confidence rambling paths with the same voting weight as flawless high-probability reasoning chains. As an interview tip, mention log probability averaging as an advanced technique for ranking and weighting self-consistency votes.
Question 9. How does self-consistency perform on open-ended creative tasks versus closed deterministic tasks?
Self-consistency performs exceptionally well on closed deterministic tasks, math, logic, multi-choice, classification, but is poorly suited for open-ended creative tasks, story writing, brainstorming, subjective marketing copy. Closed tasks have a single ground truth answer that multiple reasoning paths can converge on. Creative tasks have infinite valid outputs, so voting across 10 diverse creative stories yields no statistical consensus. For example, asking for 10 creative names for a coffee shop produces 10 unique lists with 0 overlapping votes, breaking the majority voting paradigm. A common mistake is applying majority voting algorithms to subjective or open-ended creative generation tasks. As an interview tip, state the rule: self-consistency requires a convergent answer space to perform majority voting effectively.
Question 10. How do you combine few-shot CoT with self-consistency for maximum benchmark performance?
Combining few-shot CoT with self-consistency involves providing 3 to 5 high-quality manual CoT exemplars in the prompt, setting temperature to 0.7, generating 10 sampled paths, and taking the majority vote on the final extracted answers. Few-shot CoT provides structural guidance and exemplar reasoning patterns, while self-consistency eliminates stochastic sampling noise. This combination represents the gold standard for achieving state-of-the-art accuracy on complex benchmarks. For example, achieving top-tier benchmark scores on SVAMP and math datasets by combining 4-shot CoT exemplars with 10-path self-consistency decoding. A common mistake is relying on zero-shot CoT with self-consistency when few-shot CoT exemplars could further boost base path quality. As an interview tip, present this combo as the ultimate inference time prompting strategy for state-of-the-art reasoning accuracy.
Excellent. You've completed Chain of Thought Prompting, Part 3, Self-Consistency and Majority Voting. In the next video, we'll dive deeper into using one-shot prompting to enforce strict JSON and XML outputs for API integrations. If you found this video helpful, please like, share, subscribe to SHR Trinity, and press the notification bell so you never miss our upcoming AI interview preparation videos. Thank you for watching. See you in the next video.